Hello everyone and welcome back to another episode on complete reference to CUDA programming series. So in previous episode we understood the threads and block concept in CUDA programming, how threads are organized. Just to give quick recap, we said threads are grouped together to form blocks and blocks are grouped together to form a grid. Now we'll try to execute a simple program to understand the concept of threads and block, and we'll try to retrieve these IDs inside the CUDA function. So here I'll be using the same program that we used in case of hello GPU. So we'll be having a main function here. Inside that we are calling two functions, hello CPU and hello GPU. Hello CPU is simple CPU, or you can say C function, which is going to print a statement hello from the CPU. And this is just like your normal C program, C function execution. Now here, next we will be having hello GPU function, and we can see here we are having something crazy in this triple angular brackets, and we are mentioning some parameters here. So this is supposed to be n blocks, and this is supposed to be n threads. Now here, while launching any CUDA function, we call it as a kernel, we have to mention how many threads to be created, and that we are going to mention in terms of number of blocks and number of threads. To understand this, let's try to take some cases and we'll try to assume the number of threads and blocks, and we'll see whether we are getting the same output or not. So this is your main function. I'm having hello GPU call here, and here I'm passing first parameter as number of blocks and second parameter as number of threads per block. So when CPU launches this function, immediately it will start executing on GPU. So it will call this function definition and it will start executing this hello GPU function. And at this particular line, it will get number of threads we have mentioned here. So as of now, in this configuration, we just mentioned that number of blocks equal to 1 and number of threads equal to 1. So that means as soon as it start executing this particular function, it will be having only one thread. Why? Because the configuration is like number of blocks equal to 1 and number of threads also equal to 1. So total number of threads we can calculate using number of blocks multiplied by number of threads per block. And in this case, it will be just simply 1 multiplied by 1. So total number of threads launched will be only 1 here. Now I have created one block, and which is going to have ID equal to 0, and inside that block I'll be having one thread which ID equal to 0. Why? Because in earlier episode I mentioned that both thread IDs and block IDs are indexed with starting value as 0. Now one thread is created, and now for this particular thread we are going to create some variables tid, bid and bdim. Those are integer variables which are going to store or retrieve some values for associated with that particular thread. So this particular single thread is going to create a variable tid, and that is going to be private to that thread, and which is going to retrieve value thread idx.x. So this particular statement is going to return the ID of that thread, and it will be stored into the tid. Next, we are having block idx.x, which is going to return the block ID in which that thread belongs to, and that will be 0. And block dim.x, which is going to return the total number of threads per block, and that will be stored into this bdim. Now for this particular thread, it is going to create its own copy of tid, bdim and bid. So all these three integer variables are going to hold the corresponding IDs here. And once these are stored, simply it is going to go further and execute this print statement, and it is going to print its thread ID, block ID and block dimension by using these tid, bid and bd. Note that all these variables that we have created, those are going to be private to that particular thread. That means if we are having any other thread, that is not going to modify or access the variables that are declared for this thread. So this is the first scenario where I am just simply mentioning number of blocks equal to 1 and number of threads per block equal to 1. Now if I change this configuration little bit and if I mention the number of blocks equal to 1, total number of blocks equal to 1, and total number of threads per block equal to 2. So that means I'm going to create one block, and in every block I'm going to create two threads. So total number of threads will be here again 2. Now just to give a logical view for that, this is a block, one block we created, and we mentioned number of threads per block equal to 2, and that's why I'm mentioning these two arrows inside this square. So that just to give you a logical view of how threads are organized inside a block. Now as soon as we call this CUDA function, just give me a second, we call this CUDA function with number of blocks equal to 1 and number of threads equal to 2, then at this particular point it will create one block and two threads here inside this GPU function. Now we will be having two such threads, and for these two threads independent copy of TID, BID and BDIM will be created. So for this, let's say first thread will be, it is going to retrieve this its own thread ID, and that will be 0. So TID will be 0 for the first thread. Then BID for that thread is going to be 0 because we are having only one block, so its ID is going to be 0. And finally blockdim.x is going to be returned into this bdim variable, and that bdim is going to hold that is value equal to 2 because we'll be having two threads per block. And finally this thread is going to print the corresponding values using this print statement. At the same time we'll be having next thread, that is TID equal to 1, and that is also going to execute all this statement, and it is also going to print its own printf statement here, right? So that means here we have created one block and two threads in a block, and all the threads are going to execute all these four statements. Now next is scenario is here we are going to consider number of blocks equal to 2 and number of threads per block equal to 1. Now in this case we can calculate total number of threads again simply by multiplying number of blocks, that is we are having here 2 blocks, and we'll multiply these 2 blocks by number of threads per block equal to 1 thread, right? So total number of threads will be again here 2. Now how logical it looks like, again as soon as it start executing this CUDA kernel, so it will create 2 blocks and 1 thread per block. So this is the logical view for that thread organization. Now all these threads will start executing the next statement. So this thread is going to execute TID equal to thread idx.x, so it will return 0 because only one thread is there in this block, so its ID is going to be obviously 0. Then this thread belongs to block number 0, so for that the BID value will be 0, and BDIM, which is going to take value equal to 1. So because block dimensions are going to be same for all the blocks, so it will be 1 here. Why 1? Because we mentioned while launching kernel number of blocks equal to 2 and number of threads equal to 1. Then we'll be having another thread that is from block number 1, and it is also going to execute the same statements. So first the TID is going to be 0 because earlier I mentioned the thread ID is going to be local to that block, so TID will be 0 here. Then we'll be having BID. Note that this thread is executing, but its block ID is 1 now, so it will get value as 1 in the variable BID. And block dim.x is going to return the total number of threads in a block, and that is will be 1. Note that this block dimension is going to be same in all this configuration because we are specifying that while launching the kernel itself how many blocks you want to launch and number of threads per block. So that is not going to change inside this kernel. Okay, so now we have final scenario here where we'll be launching total number of blocks equal to 2 and total number of threads per block equal to 2. So in this case I'll be having 2 blocks and total number of threads per block equal to 2, and hence total number of threads I'll be launching equal to 4. And how the logical picture looks like here, so again we are launching 2 blocks, so I'm having 2 squares here, rectangles, and first indicates block number 0 and second indicates block number 1. Inside every block we mentioned there are going to be two threads. So here we'll be having first thread and this is second thread. In block number 1 as well, we'll be having first thread here and second thread. Now all these four statements are going to execute the statements that are mentioned in this hello GPU kernel. So here let's see, we are having this particular thread which is going to execute TID, and it will retrieve its own ID using thread idx.x, so that value will be 0. Then BID value is going to be 0 because this thread belongs to block number 0. Then BDIM, that is block dimension, will be 2 because we'll be having 2 threads per block. Now same for this thread, we'll be having TID equals to 1 because this is thread 0 and this next thread will be having ID equal to 1. Now block ID is going to remain same for this thread as well, that is 0, and block dimension is also going to remain same. Now for this thread from block number 1, again TID value will be 0 and BID value is going to be 1 now because this thread belongs to block 1. And finally we'll be having block dimension which is also going to be the same, that is 2. For this thread, it is from block number 1 and its ID is going to be 1 because we have already executed this thread number 0. So next thread is going to be having ID equal to 1. Then we'll be having block ID BID, which is going to be 1 because this thread belongs to block number 1, and block dimension is as usual, it is going to be same for this thread also, right? So this is what logically threads are organized when we specify this configuration in this fashion. Now whatever these cases are there, we'll try to run using this CUDA program. So here same program is there. So first case was number of blocks equal to 1 and number of threads per block equal to 1. Now only one thread gets created. It will execute all these statements and it will print the thread ID, block ID and block dimension. So let's try to execute this and we'll see what is the output here. We have hello from CPU and only one thread is created. So its ID is thread 0, block ID is 0 and block dimension equal to 1. Now what I'll do, I'll change this parameter number of blocks equal to 1 and number of threads per block equal to 2. Now in this case, total number of threads will be launched equal to 2 and one block is created which is having ID 0, and inside block 2 threads are created which are going to have ID 0 and 1. So let's try to see whether we are getting same output or not. So if I execute this, you can see we are having one thread is created with ID 0 and other thread is having ID 1. Note that here both belong to same block, that is block number 0, and block dimension are going to be the same because we have launched only one block with 2 threads per block, right? So here we created 2 threads. Now let's change this parameter and we'll make sure here 2 blocks I am going to launch and only 1 thread per block. Now we are having 2 blocks and 1 thread per block. So if I execute this, I'll execute here so that we can differentiate. So you can see now we have 2 threads, both are having ID 0, but their block IDs are different. So this is thread 0 from block number 0 and this is thread 0 from block number 1 because we have launched 2 blocks with 1 thread each. Now I'll change this parameter as 2 blocks and 2 threads per block. So let's say if you execute, what would be the output? So I'll execute here and you can see now I'm having total number of threads execution equal to 4. 4 threads executed these statements, and we have this thread 0 from block number 0, thread 1 from block number 0. Then I'm having thread 0 from block number 1 and thread 1 from block number 1. Right? So this is how the threads are organized in case of CUDA kernel. So key takeaway from this is whenever we launch any CUDA function that we call as a kernel, we have to specify a number of threads to be created because we have to create many threads and many threads can be executed in parallel, so we can assign different tasks to each thread. Now threads are organized in terms of blocks and grid, and we have to mention the thread configuration in terms of number of blocks I want and number of threads per block. If I want to, let's say, launch 10 threads, then I can launch in various configurations. So for example, if I want to launch 10 threads, so I can say number of blocks equal to 10 and one thread each block. That will give me 10 threads. Or else I can change the configuration as one block and 10 threads per block. This will also launch 10 threads, but in only single block, right? So same way I can launch, let's say, 2 threads, 2 blocks and 5 threads each. So this will also give me 10 threads. So if I execute this program, so you'll see that here I have launched 10 threads, but 5 threads each block. So this is block number 0, where we are having 5 threads, and this is block number 1, which is having 5 threads. I can reverse that also. I can have 5 blocks here, and I can launch 2 threads per block. This will give me 5. This will give me 5 blocks here. So we are having this block number 0, then we are having block number 1, then block number 2 is there, which is having 2 threads, then block number 3, which is having 2 threads, and finally block number 4, which is having 2 threads. Note that here order in which they are executed is completely random, right? Because we don't know which thread will start executing the printf statement first, because our job is to create, let's say, 10 threads, and the 10 threads automatically get scheduled in parallel, and whichever gets output terminal first, which is going to print the statement that is mentioned in the printf statement, right? So this is how threads are organized. So remember that whenever you start launch any CUDA kernel, you have to specify number of threads in terms of number of blocks and number of threads here. And whenever this hello GPU function start executing, exactly same time these many threads are created, and all the threads execute in parallel, and all threads will start executing these statements independently, right? So that's it for this particular episode about thread organization. In next episode, we'll try to solve actual problem using this CUDA kernel. As of now, we just understood thread and block organization. In next episode, we'll take a vector addition program and we'll try to parallelize it using these threads, multiple threads.